In this section, we're going to learn that if I have a function f and a function g, I can check to see if they're inverses of each other. And the way I do that is I take the composite function f composed with g, and if it equals x, and then I take g composed with f, and it equals f, then they are inverses. But notice you must have the word and. It has to meet both of those requirements. Let's check these. Our first problem gives us function f and function g. So first we're going to check f composed with g, and next we're going to check g composed with f. Both of these need to equal x for f and g to be inverses of each other. So let's just see if that's true. So f composed with g, that's the same thing as saying f and then putting g sub x as my input. Okay? So f of x is equal to 2x minus 1 divided by 3. And f of g sub x means wherever I have an x, instead I'm going to put g sub x. So g sub x is 3x plus 1 divided by 2. So let's go ahead and multiply that out. That's going to become 3x plus 1 minus 1 over 3. So 3x plus 1 minus 1 will become 3x divided by 3, which is equal to x. So far we are correct, and we do have f composed with g is equal to x. But I have to check the second requirement, g composed with f. So g composed with f, an open circle, is equal to g and then of f of x with as my input. I can rewrite this as g, and then in place of f of x, I'm going to write 2x minus 1 divided by 3. I know that g sub x is equal to 3x plus 1 over 2. So g sub 2x minus 1 over 3 means wherever there's an x, I'm going to put in 2x minus 1 over 3. And I can see that this will become 2x minus 1 plus 1 all over 2, 2x divided by 2, which is equal to x. So this also checks out. So both of these requirements are met. So since f composed with g and g composed with f are both equal to x, we know that g is equal to the inverse of f, and f is equal to the inverse of g. Our next problem gives us a function, and it asks us to find the inverse of the function. We know that a function can only have an inverse when it's 1 to 1, and we notice that the domain here is limited to x is greater than or equal to 5 halves. So this will make sure that we don't ever have a radicand that is less than 0. So we can see that this is 1 to 1. Every output will only have one input, and it is a function. So it does meet that requirement of 1 to 1. To get the inverse, I'm going to replace f of x with y. And now I'm going to swap. Wherever there's an x, I'm going to put a y. And I'm going to solve for y. So I'm going to square both sides. And I'll get x squared is equal to 2y minus 5. Okay, so I'm going to add 5 to both sides. And I'm going to divide by 2. And then my last step, I'm going to replace y with the inverse of f of x. Part B tells me to find the domain and range for both f of x and the inverse of f. So whatever my domain is becomes my range of my inverse. And whatever was my range becomes my domain of my inverse. So for f of x, we know that our domain is 5/2 to infinity, and our range is 0 to infinity. And I can get this, if you're struggling with the range, one way you can do it is by graphing it. Another is plug in the endpoints. Plug in 5/2, and you'll see that will go to 0, right? So it's going to go from 0 to infinity. Now, the inverse is going to just swap my domain and my range. So my domain now will be 0 to infinity, and my range will now be 5/2 to infinity. Part C asks us to graph f of x and the inverse of f. So to graph this, I'm just going to put in a couple points to kind of help me. So I put in this number. So this is going to be the function f of x. So I use these table values, and I just use my calculator to figure out approximately what square root of 5 is and what square root of 15 is. Now, to graph the inverse function, I can do it two different ways. I can just take this same table and swap the x's and the y's, right? So I can change this to be 0, 5/2, and the square root of 5, and then 5, and then square root of 15 and 10. That's one way. Or I can remember that the inverse and the function are symmetrical about y is equal to x. So I could draw this line in, and then I could just draw the symmetrical points. It's really up to you. And I'll get something that looks like this, and you can see that it's symmetrical about this y is equal to x, the identity function. So this would be my inverse function, and this would be my regular function. Okay, our next problem, we're going to do the same thing. So we know that a function and its inverse are symmetrical about the y is equal to x line. So I'm going to draw that one in first. This is y is equal to x. Now, if I want the inverse, I can use these points here. This is 5, 3, and this is 9, 5. I can use them, and I can just swap the x and the y. So I'm going to graph 3, 5, and 5, 9. Remember, they're symmetrical about this. So if you're getting confused, think about if you drew paint on this function, if you painted this, and then you folded the paper along this y is equal to x and smushed it together, then you would get this over here. This is going to be f. This is going to be my inverse. Find the inverse composed with f. Okay? So we're going to find the inverse composed with f. We could write that as the inverse, and then our input could be f at 5. So let's think what that means. F at 5. So if I go to when x is 5, then our output will be 3. So that's equal to 3. And then I have to say, what is my inverse at 3? Well, my inverse at 3 will be 5. You can see I go up from here to this one, and I'll get 5. Let's try the next one. So I have f composed with the inverse at 5. And I like to write it myself like this. That helps me see that first I start with what is the inverse at 5. So I'm going to start at 5, and I'm going to go all the way up to the inverse, which is 9. And then I say, what is f at 9? So I go over here to 9, and I go up, and it's going to be 5. For a word problem, so I'm going to give you a second to pause the video and to read this. So we've read the problem. We see that Gerard is studying about how food works, and he has eaten 1,070 calories, and then he went and burned 584 off per hour. So he's created this function, r of x, which tells him the total calories remaining after playing x hours of basketball. So it says, A, interpret what r at 0.75 means. So I'm going to take my function, and I'm going to replace x with 0.75. And I get 632 calories. So this means that after playing basketball for 3/4 of an hour, there'll be 632 calories remaining. Now let's look at part B. Part B says find and interpret the inverse. So to get the inverse, we're going to change R of X into Y. And then we're going to swap the X and the Y. And then we're going to solve for Y. And then last but not least, we're going to remove the Y and replace it with the inverse of X. Now, when it asks us to interpret what this means, we have to remember that our X and our Y got swapped, and so did the meanings. So X was the number of hours of basketball playing, and Y was the total calories remaining. Now it's going to be the opposite. This is going to be the calories remaining. So the inverse is going to tell us if we have a certain number of calories remaining, we'll solve for the number of hours of basketball that will be played. So you can see that the input and the output get swapped when you're looking at the inverse. Now let's look at part C. Find and interpret the inverse of R at 100. So we have the equation, and so we're just going to change out the X of 100. And we get 1.66 when we're rounding to 2 decimal places. And this means to have 100 calories remaining, you must play basketball for 1.66 hours. And then last, verify algebraically that R and R1 are inverses of each other. So we're going to see what R composed of the inverse. We want to verify that it's equal to X, and that the inverse composed with R is also equal to X. We'll check both those out. So for our first one, I like to write it out like this. So I'm going to take my inverse function and put it into the inputs of my original function. So I'm going to say 1070 minus 584, but in place of X, I'm going to put X minus 1070 divided by negative 584. And I can see that the 584 and the 584 will cancel, and I'll be left with a plus. And I can see that 1070 and 1070 will also become 0, so I'll be left with X. So far we're looking pretty good. Now let's check the inverse composed with R. So I like to write it out like this to remind myself which order to put it in. So I'm going to take my output of R of X, and I'm going to put it into the input of the inverse. So instead of X minus 1070, I'm going to put 1070 minus 584X minus 1070 divided by negative 584. And I can see that I'll end up with negative 584X divided by negative 584, which is equal to X. And so this checks out also. It's our lucky day. We have one more word problem. So I'm going to give you a moment to read it. So pause the video. Okay, so it says, is h of x a one-to-one function? So we can just quickly kind of sketch what we know it's going to look like. We can see that it's a quadratic, right? So we know that it's going to go down, and it's a quadratic like this. So it is definitely a function, but it will not pass the horizontal line test. But they restricted the domain by saying x is greater than equal to 0. So by adding this restriction, now it is also going to pass the horizontal line test. And since it passes the horizontal line test and it's a function, it is one-to-one. Next, it says find and interpret h at 2.8. So we're going to take our function, and wherever there's an x, we're going to replace it with 2.8. Now, the problem tells us that as the function's written, x is the time in seconds. So after 2.8 seconds, Vince is 49.56 feet above the water. Part C asks us to find and interpret the inverse of h. So to find the inverse of h, what we do is we take our function and we replace h of x with y, and then we swap our x and our y, and we solve for y. And I will get y is equal to the square root of x minus 175 over negative 16. And since we took a square root, we're going to consider both the positive and the negative. So this is a good problem to think about those domains and ranges that we talked about in the last section. So we know that our domain of our function of h, our domain is 0 to infinity. Okay? And we know that our range will be from negative infinity to 175. And I know that because I just went ahead and quickly put it in my calculator, but I can see that this parabola looks like this. And the vertex right here is at 0, 175. So the lowest is negative infinity, the highest is 175. So when I want to look at my inverse, which I have here, I want to be mindful of that because I know that my domain of this and my range are going to basically be swapped, right? So my domain will be from negative infinity to 175, and my range will be from 0 to infinity. This will also, though, keep me from having a radicand that's less than 0. So you can see now I'm only going to use the positive side because of my range is only going to be positive values. So my inverse, notice I'm only going to use the positive values. Part D asks us to find the inverse at 100. So we're just going to take our function here and evaluate it for 100 for x. And I'll get that it's approximately equal to 2.17 seconds. The inverse tells us that at 2.17 seconds, after he jumps, that he will be 100 feet above the water. Part D asks us, when will Vince and his friends reach the surface of the water? Well, we know at the surface of the water, their height will be 0. So we're just going to set our original function equal to 0 and solve. This is a quadratic, so we could solve it in many ways. You could use the quadratic formula. You could try factoring, but I don't believe it's factorable. You could try the calculator. I'm going to use the square root property, and I'm going to subtract 175 from both sides and divide by negative 16, the square root of both sides, and I get plus or minus 3.31. But we have to remember this represents seconds, and time can never be negative, so we're only going to look at the positive root. So 3.31 seconds. Part F asks us to graph the function h of x. Part F asks us to graph the function h of x. So h of x was simply our quadratic. However, we're limiting our domain to greater than or equal to 0 for x. I know that my roots I just solved, so I had 3.31, so I'm going to go ahead and put that one on here, somewhere in there. And then I know my vertex, well, I don't need a calculator. I could use the vertex formula, but I could recognize that this is in vertex form. Whenever I don't have an x term, I recognize it's in vertex form, and I can see that my vertex, my hk, will be 0, 175. So I went ahead and graphed h of x, and I added in a point at 2 too, just to make it nice and clean and make sure it was the right shape. And then last, we have verify algebraically that h and the inverse of h are inverses of each other. To verify this algebraically, we know that h composed with the inverse of h will equal x, and then the inverse of h composed with h will also equal x. So let's check that. Let's check the first one. So I replace the inverse of h with the square root of 175 minus x over 16 from our earlier part of the problem. And now I'm going to write h, which is negative 16x squared plus 175. And I'm going to instead, I'm going to replace anywhere there's an h, I'm going to put square root of 175 minus x over 16. And I can see that I'll get negative 16, and this will become 175 minus x over 16. And when I multiply that out, I'll get x. So that does check out. Now I want to do the other direction. I want to say, what about when the inverse is composed with h of x? Let's replace h of x with its function value. And then I'll write my inverse equation, replacing any x with my h of x value. And I will simplify this. So this will become 175 minus 175. That will become 0. And I'll end up with 16x squared over 16, all beneath the radical, which we know will become the square root of x squared, which is x. So this will also check out. And so they are inverses.